We'll quickly say how to do the how we did this particular experiment in the lab. So the system that we are focusing is, it's not the salicylic acid, it's salicylamide. I think before I said salicylic acid, it is salicylamide. Then we are going to crystallize in presence of ethyl acetate. Going to crystallize in presence of ethyl acetate. So we are going to nucleate. We are going to perform the nucleation experiment. Everything at 15 degrees centigrade. And then the supersaturation, no, the solubility of a salicylamide at this particular temperature is, is equal to around 2.23 grams per 20 milliliters. So this is your solubility limit at 15 degrees centigrade. So what we are going to do is, like, we are going to perform the nucleation rate. We are going to perform now. We are going to perform some nucleation experiment in order to calculate the nucleation rate J at different supersaturations. At different supersaturation, say like supersaturation of 1.3, then supersaturation of 1.5 roughly, supersaturation of say 1.76, supersaturation of 2.0, supersaturation of 2.26, supersaturation of 2.57. So we need to calculate the G value as a function of supersaturation. So why we need to do this, we will understand at the end of this experiment, or once we finish with our calculations. So we need to calculate. So what's the effect of your initial supersaturation on the nucleation rate? Normally the rule of thumb is like, higher the supersaturation, higher will be the nucleation rate, which means your how do you call it? The concentration of your solute in the solution is very high, so that how high in the sense like, so if let me put it this way, so C is greater than C star when S is equal to 1.5 and S is equal to 2.57, which means C should be much greater than your solubility values. So which means your solid molecules, they likes to come together and then they should eventually settle into a stable nuclei. So which means the nucleation rate should be much higher. So because if you have a solution which is higher than your solubility limit, then all the molecules, they likes to come together. More likely is the molecules, they will come together. So if the supersaturation is higher, more and more molecules will come together. Eventually they all settle into a stable nuclei. So this will be, say this is say like 1 2 3 4 5, say 5 nuclei per unit volume per minute. And if you have slightly a low supersaturated solution, say S is equal to 1.1, so it is less likely when you compare to the above. And then eventually they will also settle, but this time it will be somewhere around 3 3 nuclei per unit volume per unit time. So that's the whole idea of nucleation, and we are going to exactly calculate what will be the nucleation rate if your supersaturation is 1.3, what will be your nucleation rate if your supersaturation is 2.57, and so on. So we all know that nucleation is a probability, something like it's like a probabilistic event. So or if you want, we can say it like it's a stochastic process. So we have to perform obviously a large number of experiments in order to get reasonably decent statistics, and also to capture accurately the not accurately capture uh, like capture the stochastic event in a more reasonable way. Like you cannot, for example, if you take a supersaturation of 1.3, you cannot do just two experiments, just to take a 2 vial and then you take the supersaturated solutions, maintain at 15 degrees centigrade, and wait until these two vials nucleate. Yeah? So this vial may nucleate say 2 minutes, and this vial say it nucleates in 2 days. So what will happen in between? So 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 our general idea will be like, the probability of the one vial getting nucleated is 2 minutes, and the probability of 2 vials getting nucleated is 2 days. Yeah, so this is not a good statistics. So that's why we have to do multiple experiments. So what we did in the lab is like we used 40 vials. So just assume we did 40 vials, 1, 2, 3, and then this is your 40th vial, and then we have to work, say like let's we are working with a super saturation of 1.3. So this 1.3 will not come just like that in the solution. We have to create the super saturated solution. So we know the solubility of this compound at 20 degrees centigrade is 2.23 grams per 20 ml. So if you need to create a super saturation of 1.3, we know the formula. Super saturation ratio is equal to C by C star. So C will be equal to S multiplied by C star. So give me a second. Let me change the pen. So just to remember all these formulas. So we know supersaturation is say 1.3. Supersaturation is 1.3. Therefore, the amount of mass that we need to create this amount of this level of supersaturation ratio will be C is equal to 1.3 multiplied by your solubility concentration, which is 2.23 grams per 20 ml. So this will be equal to C will be equal to what will be the amount of, let me check this, 2.23. So all we need to do is just multiply this value multiplied by 1.3. So that will be roughly around 2.9 grams. So 2.9 grams in 20 milliliters of ethyl acetate. So ethyl acetate is nothing but our solvent. So we are just checking the nucleation rate of salicylamide in ethyl acetate. So we have to dissolve for sure 2.9 grams of salicylamide in 20 milliliters of ethyl acetate solution. So this is how. So if you mix this one, so obviously you cannot dissolve this many gram in 20 ml at 15 degrees centigrade, because this is something above your solubility limit. So normally what we do is like we raise the temperature 15 degrees centigrade to plus 5 degrees centigrade. So that will be 20 degrees centigrade. At this particular temperature, everything should be dissolved. Sometimes we even heat to 20 plus 20 degrees centigrade. But normally for nucleation experiment, we won't go more than 5 degrees centigrade. So 15 plus 5 degrees centigrade, that will be 20 degrees centigrade. So how we do this experiment? To do the experiment, we need 2 water bath. So we need 2 water baths. So this is 1 and then this is 2. So in one of these water baths, we will have something to place our vial, 40 vials. And then normally we place the vial and then we stir the vials using a magnetic stirrer. So there will be 40 vials in this bath, and this temperature, the temperature in this water bath will be maintained at 20 degrees centigrade. So what we do is we take 40 vials. In each vial we add exactly 2.9 grams 2.9 grams of salicylamide, and then 20 ml of ethyl acetate. So we close the vial and then we put this in the first water bath, which is maintained at 20 degrees centigrade. Let's call it as like a heating water bath. So this is water bath 1. So and then we wait for say 1 hour. So in this 1 hour, everything will be dissolved. So this is at 20 degrees centigrade, everything will be dissolved. So and then once after 1 hour, what we are going to do is like we will we need one more water bath. Here we have the same setup so that we can move the vial and place it to the second water bath. You don't have to label any of your vials. There is no need to label them because the which number nucleate first, that doesn't matter. All we are focusing is how many vials nucleated at any instant of time. So we are going to transfer the vial from the first bath to the second bath at the end of the first hour. So at the end of 1 hour, sorry. So so the second water bath will be maintained at 15 degrees centigrade, and we are going to estimate the, the nucleation rate at this temperature, which is 15 degrees centigrade. Let's call it as a working temperature. So automatically, once your solution drops to 15 degrees centigrade, you will naturally achieve your supersaturation. So you know the reason, because I already explained to you how to create a supersaturation in our virtual lab video. So this one should create 1.3. That's our supersaturation. So once you place the vial, once the solution reached 15 degrees centigrade, supersaturation will be equal to 1.3. And then what we are going to do is like we will place a camera in the top of the second water bath. So this camera should have a good view to all the vials. If you have 40 vials, this camera should show us all the 40 vials. What we are going to do is like we are going to record. So once we place all the vials, we switch on the magnetic stirrer. So all the vials will start to stir. So you will start your agitation all at the same time, and then you will put a camera, and then from the camera will record. So you can go to home if you want. So you can come the next day, and then you can check the film, and then check. You can play the recorded video, and then you can calculate at what time you started your agitation. Say time t equal to 0, and from there we can see at what time the first vial nucleate, and what time the second vial nucleate, at what time the third vial nucleate, and so on. So once you did this experiment, so from the from the video you have to get this experimental fact. This is something, it's not even a measurable, it's something like a visible. You use your naked eye to see when the nucleation happened. So it's very simple. If you look at the video, which I will append to this video. So once I finish talking about how we did the experiment, I will upload the video of the actual experiment which is performed at this particular supersaturation, and then I will even show how I will play the video which was recorded using this camera, and then you will see in real time how the vials nucleated. So how the solution turned from clear solution to cloudy solution. So you act like, so normally we check the concentration using UV spectroscope and so on, but for nucleation experiment we will be something like the how do you call, instead of using analytical probe, we will be the person, we will act like the sensor. So we will look at the vial, and then we tell, oh, at this time I see the solution changed from clear to cloudy solution. So which means my first vial got nucleated, and this happened when time t is equal to say 2.5 minutes, something like that. So from from the video, all we need to generate is time, what time it nucleated. So say, so a number of vials nucleated, and then we have to take, you will have some 40 points here, and this will be at the end you will have 40 vials. All the vials will be nucleated, 40 vials will be nucleated, and then from there we can calculate this probability of vials getting nucleated. This is just simple, yeah, like which how many number of vials nucleated divided by total number of vials multiplied by 100, or if you want, you don't have to multiply it by 100. If you don't multiply it by 100, the probability will range from roughly 0 to near 1. Sorry, to 1, 0 to 1. So 1 means all the vials are nucleated. And then all we need to calculate is the nucleation rate using the probability function, which I already explained. So I hope you all know understand how we do the experiment, and then how we get this nucleation rate and so on. Why I'm doing this is like, normally if you see the textbook, you will have some problem like, oh, somebody did nucleation of some API compound in that particular solvent, and then we suddenly estimated a nucleation rate of say like 10,000, something like 10,000 1 divided by meter cube per second. So something like 10,000 is roughly nuclei per meter cube per second. You will get some number like this, and then they will never tell how this number was obtained, and you will never know like this G value is something related to your probability function, and it is related to your probability function, and that's because nucleation itself is a stochastic process, and all we can measure is only the probability of nucleation. There is no precise number when it comes to nucleation. You can get some number like that may be connected to the number of nuclei per unit volume per second, but there is not. So this is like if you do this experiment, if you perform experiment with 40 vials, G value will be some number, and if you the more the number of vials we use, more and more will be the this more and more will be the precision of the J value that we calculate. So keep these things in the mind. So, but normally in the lab we do up to 400. Some people they do up to 300 vials. It depends on the level of sophistication we have in the lab and the time we have. So I think so far so good. So what I'm going to do is like I'm going to append a video of the real experiment. I didn't do the experiment. Shubangi did that experiment. So you will see her like so what she did is like she placed the vials in the heating bath, and then all the vials we added the right amount of salicylamide, and then we added the exactly 20 ml of our solvent, in this case which is ethyl acetate. And then what we did is like we heated the solution to 1 hour. So after 1 hour she is transferring to the working the bath, which is maintained at the working temperature. So I will add this part of the video, so you will see Shubangi placing her vials in the vial which is maintained, sorry, in the bath which is maintained at 15 degrees centigrade. This is the working temperature, and then she put a camera to record whatever happened after that. So I took the video from that camera, and then that's what you are going to see. So that this video will give you some idea how stochastic this nucleation can be. You will see that not, not all the vials will be nucleated at the same time, but it will be like one vial get nucleated at say like 2 minutes, another vial get nucleated at 40 minutes, and so on. So it's a very long video, so I will cut it short. I will try to edit the video so that I will say at what time the first vial nucleated, at what time the second vial nucleated. So if you don't want to see it, you can just fast forward the video, and then you can just go directly to the calculations. But I recommend you to watch the video so that you will have a sense like, okay, now at least if somebody asks you what is nucleation, at least you know that you have to believe your eyes, and with that you know, okay, I can tell at this particular time this vial nucleated. So at least you won't think like I have no clue when somebody says like my solution got nucleated. Yeah, when you see the video you will understand what do you mean, what's mean by my vial reached the nucleation point. So before discussing about the results, I just want to show the experimental setup that we normally use in the lab. So as I said before, like we have normally we need two different water baths. So this is something like assume this is a water bath, and inside the water bath we can place something like a magnetic stirring plate. So we need two of them. So, and this T suffix n, it means like a nucleation temperature. So this is the temperature, or if you want, we can replace T suffix n with T suffix w, which means something like a working temperature. So this is the temperature at which we are going to calculate the nucleation rate here. And this is, you need this bath to prepare the supersaturated solution, because to create a supersaturation, we need to add obviously some mass in excess to that of solubility, and obviously you cannot dissolve that mass at a solubility temperature. So we have to raise the temperature. So in this case, 5 degrees centigrade. So, and then what we do is like we add, as I said, we will add all the APA compound, 20 ml of your ethyl acetate solution, and then we place the 40 vials in the stirring plate, and then we stir at 15 plus 5 degrees centigrade. That will be 20 degrees centigrade. So we stir it for 1 hour. So once everything is dissolved, 1 hour is more than enough to dissolve all the compounds that we are adding. And then all we're going to do is like after 1 hour we will stick to the next. We're going to use the second bath, and this bath is already maintained at 15 degrees centigrade. So, yep. so so what we will do is like we will suddenly, like at the end of 1 hour, you will move each vial from this side of the bath to the next side, and then we will put a camera here. We will put a camera, it can be anywhere, but we should place the camera so that the camera can view all the vials in the stirring plate. So that's the goal. And then this camera will record, so whenever the solution changes from clear to cloudy solution, so obviously this will be recorded in the camera. So, and anyway, camera, we also have some play time. From that time we can calculate, okay, at time t equal to 0, this vial got nucleated. Some other time, sorry, time t equal to 1 minute, this vial got nucleated, and some other time another vial got nucleated, and then next time, after some time interval, the third vial somewhere here it got nucleated, and then we are going to record. That's the time, and then the number of vials nucleated. Yeah, sometimes 2 or 3 vials can nucleate at the same time. So at that time we have to write like so. At that particular instant of time, say three vials nucleated. So it will be like you have to add the vials, first vial, second, third, and then if 3 vials get nucleated, it will be 4, 5, 6. So 6 vials nucleated at that particular instant of time. And I think Shibangi she put something like light, because I remember she used a LED light. She put a LED strip throughout the water bath, so that when you record through the camera, that light will show how the solution turned from clear to cloudy solution. So this is really important. We need a very good camera, and we should have enough light inside the water bath, so that whatever the changes that is occurring in the solution, that can be captured using a normal digital camera. So that's the experimental setup. so so what we did is like, or what Shibangi did is she did this type of experiment. Like she started with 40 vials in the first water bath, and then after 1 hour she moved to the second water bath, and then she monitored the time at which all like each vial got nucleated until she observed nucleation in the 40th vial. So that's the experiment. And then she did this experiment for 5 different supersaturations. So I think it's 1.3, 1.5, supersaturation of 1.76, supersaturation 2, 2.26, and 2.57. So this is like a very laborious experiment. I think she might have spent nearly 2 to 3 weeks to finish all these experiments. And then we have the data already. So what I'm going to show you is like the real data that was obtained in the lab, and from there we are going to calculate nucleation rate, and then we are going to apply the classical nucleation theory, and then we are going to calculate the pre-exponential factor, and then we are going to calculate the surface energy, and also we are going to calculate that it gives free energy. So these are the things that we are going to do now. So let's go to the experimental results. So, so Shubhang already she sent me the data. So this is some experiment which is performed at an initial supersaturation of 1.3. So 1.3. So that's the starting temperature. So what's really happening? So this is what she observed. So number of vials nucleated when time, where the first vial got nucleated when time is equal to 708. So this she converted the time into seconds. So time is expressed given in seconds. So 708 seconds the first vial nucleated, the and then 718 the second vial nucleated. If you see the video, I added something like a notation on the like on the screen, like when the first vial nucleated I put this value 708 seconds, 719 seconds, when 804 seconds third vial nucleated, and so on. And almost the 40th vial it got nucleated at, or the all the 40 vials got nucleated when time is equal to 20142 seconds. So how many minutes is that? It's roughly 335 minutes. So again by 60. So it's a lot of time. Yeah? So it's a significant amount of time. So we have to wait. That's why we cannot sit in front of the water bath. That's why we are installing the camera. So normally once we transfer the vial, which we saw in the video. So once you transfer your vial from the first water bath to the second water bath, which is at 15 degrees centigrade, and then we switch on the agitation, and then normally we go to home. This is more or like a overnight experiment. So we have the number of vials nucleated. From there, we can calculate the probability of the vials nucleated, yeah, or the probability of nucleation, if you want to put it in a simple way. So out of 40 vials, if only one vial got nucleated, then the probability is just 1 divided by the total number of vials. In this case is 40. So let's put 1 divided by 40, and this whole value multiplied by 100. So I'm just doing these calculations because it's very tough if you start from scratch. So I will do the calculations for you. So what does that mean? So this is like a 2.5 percentage of the vials got nucleated, and when time t is equal to 708 seconds, that's what it states. And then when time t equal to 2014 seconds, 100 percentage of the vials got nucleated, which means 40 out of 40 all got nucleated. So that's the meaning of that. If you want, you can express in terms of so this is expressed in terms of number, something like a 2.5 to there is some. Okay, I can remove the percentage. So if you see 0 to 1, so 1 means 40 out of 40 vials got nucleated. So we can also express this in terms of percentage, just multiply it by 100. Normally probability will range from 0 to 1. 1 means like 100% probable, and 0 means nothing. So that's the meaning of that. So what is this experiment states to us is like, if you start an experiment with the solution of supersaturation 1.3, and if you're going to perform that experiment in a 20 ml solution, so this will be roughly, it is equal to 0.0002 meter cube. We just converted ml to meter cube of solvent. So then the probability of the nucleation for 100% nucleation will be around this number, or in other words, the nucleation can occur somewhere between this time interval, like from 708 seconds to 20142 seconds. So that's the meaning of that. So your solution might nucleate somewhere between this time interval. Yeah, it can be 708, maybe all the vials got nucleated, or maybe only 2.5 percentage of the vials will get nucleated. So this is something like a chance of nucleation is 2.5%. At this time, chance of nucleation is 100 percentage. So if you want, you can call P of t. If you don't know how to call it, just call it like a chance of nucleation. So chance of nucleation is 2.5 percentage, which is less likely. and if you come when you allow some more amount of time, then the chance of nucleation is more likely. It can even be 100%. Obviously, this range will differ, depends on how many vials we use. Yeah. So if you if you have really patience and if you think you can do your PhD all your life, then you can put even 1,000 vials. Who is going to stop us? Huh? So that's the meaning out of that. And then from the from the probability or the chance of nucleation, which ranges from 0 to 1, we are going to calculate the nucleation rate. So, and here I showed a plot. So here I plotted something like, oh, this is not J, this is time. Time expressed in seconds. So this is time in seconds. And this is your chance of nucleation, like a 0 to 1. So I just plotted these two values. So time versus probability of your nucleation. So insert. So that's the graph which is shown here. So what we are going to do now is like we need to calculate the nucleation rate using this probability function. So this function will allow us to roughly estimate the nucleation rate with respect to. So this equation contains Tg. Tg is the nothing but the time when your first vial nucleate. So this is more or less like a relative probability. So based on when your first vial nucleate, from there we know when all the vials got nucleated. So this function which allows you to calculate the nucleation rate. If you ask if this is the correct way to get the nucleation rate, this is one of the many ways to get the nucleation rate. If you have a probability, so you can use this type of functions. So there are obviously so many methods. We can take the mean value. From the mean value, we can also get the nucleation rate. But for this module, just to learn this one technique, it's a very simple technique. Obviously, you need an Excel sheet to do it. So let's do this. So let's assume you plotted these values. Not plotted, so let's calculate it. So to calculate this value, we need to know the J value, but we don't know. That's what we are going to calculate. So for a beginning, let's assume the nucleation is something like 1 nuclei per meter cube per minute. Obviously, this is very low nucleation rate. For the moment, just assume the nucleation rate is 1 nuclei per meter cube per minute. So this is like something like an initial guess value. Volume is an experimental quantity. We know it's like an experimental condition, in fact. So it's 20 ml or it's 0.0002 meter cube of solvent. And Tg value, this is an experimental value. So this will be equal to 708. And then, so this is nothing, let's delete. So let's apply this equation. So this will be equal to 1 minus exponential of minus J value. If you put the dollar symbol, which means when you drag this value everywhere, it will be the same J value. So you have to use the dollar symbol, J multiplied by again your volume. If then apply the dollar symbol and then multiplied by time. This is our experimental value. This is T 708 minus this Tg value, which is here. So again you have to press the dollar symbol. So whenever you have something like a constant, you have to apply dollar symbol on the cell value. If it's before, you apply dollar symbol, so which will make this number as constant. If you apply dollar symbol, which will make this number as a constant. So that's the meaning of. I hope you all know how to use an Excel sheet. So let's close this bracket. Yes, everything looks fine. So just double click, so you get some value. So what it says is like so if your nucleation rate is equal to 1 nuclei per meter cube per minute, this will be the predicted value. So obviously this deviates from the actual experimental value. So we are going to calculate the error distribution between the predicted value, probability, which is here, which we calculated using this particular function. which is bold. I put it, let's change some color. So I'm going to go a bit slow because it's very tough. So that's the probability function which we used, and we assumed an initial j value, but we have to calculate the correct value. So how to calculate that? For that, first we have to calculate the error distribution between this value which is obtained from the experiment and the orange one which is predicted using this particular equation and for assumed j value of 1 nuclei per minute. So the error will be equal to this probability predicted value minus the actual experiment value which is here. That's the error function. So just so this is the error distribution between, like, your actual value should be 0.025 but we get only 0, so the error difference will be 0 minus 0.025. Just so you do the same for all the values. So you just subtract the predicted value minus the experimental value when the number of vials nucleated is equal to 4, and then finally all you need to do is you have to sum the value. You just sum all of these values, just sum this value. So this is something called as a sum of the errors. So what we are going to do now is like if we are going to minimize this error to 0. If the error, imagine like if you have a 0.075, that's your experimental value, and if the predicted value is also 0.075, then the error will be 0. So that's what we are going to do now. What we are going to do now is we are going to minimize the error distribution between this actual experimental value and this predicted value, this orange color line. So that's what we are going to do. So we already calculated the error between each of these points, and we are going to minimize those error. How to do that? We have to go to data, click the solver here, and then click set objective function. Click the mouse there, and then click this value. This is the sum of the errors which we calculated now. Just click it, and then select the value of 0. So what we are going to do now is like we are going to do some mathematical iterations. So we are going to make this value to near 0, value of 0, by changing j value. So what we are going to ask the Excel sheet is to perform a series of iterations, like change the j value until the error distribution between the real experimental data and the predicted function, which is p of t, that will be like almost matches with the experimental value. So you select, we have to change the j value. That's what we are going to predict now, and then just press the solve button. So what you get is something like this one, you see. So what it says is like now the error is almost 0.000000, something like that. So which means the error distribution between your real experimental value and then the predicted value is minimum to the near to 0 value. And so in this way you calculated the nucleation rate. This is the correct nucleation rate which we calculated using this technique. This is something we call it as a nonlinear regression technique. Nonlinear. I know chemical engineering students, they learn this in their first year or second year, I'm not sure. So this is called, sorry, nonlinear regression technique. This is called nonlinear regression technique. So what we calculated is we calculated the nucleation rate. So when the supersaturation is 1.3, our nucleation rate will be equal to 13.65, something like that. So normally we don't use this fractions. Now, if it's 13.6, we just put 14. We normally nucleation rate will be expressed in terms of integers rather than decimals. Yeah, there is nothing called as 1.4 nuclei, or there is nothing called as 2.6 nuclei, something like that. Yeah, it will be like a definite integer, like 1 nuclei, 2 nuclei, something like that. So okay, anyway, so for the moment I'm just going to leave 13.65, and then we can change later to some integers. So what we did is like So we did experiment like five different experiments. So each experiment contains 40 vials. So this is one experiment which it did at supersaturation ratio of 1.3, and the corresponding nucleation rate is 13.65. And likewise, Shashibangi, she did 1, 2, 3, 4, 5, 6 experiments in fact, and then she did another experiments. It's like this time S value, S is equal to 1.5, and then I already did the calculations here. Then the J value is 19.5, and then when we did the experiment, when S is equal to 1.76, so we have some other nucleation rate 26.59, and then when S is equal to 2.0, the nucleation rate is 35.55, something like that. And then when S is equal to 2.26, the nucleation rate is 99.455. And then when S is equal to 2.57, the nucleation rate is 122.47. So if you look at this one, if you see here, when the supersaturation is high, the nucleation rate is high. So the number of nuclei formed in the unit volume of solution per unit time, that will be equal to 122. Sorry, that will be higher if you start with a higher supersaturation. Say like for supersaturation is 2.57, then the nucleation rate is 122. And if you come back here, if the supersaturation is 1.3, then the nucleation rate is only around 13 point, roughly 14 nuclei per meter cube per minute. So that's the thing that we have to calculate. So now we have some values, like here I already summarized the result. So this is our supersaturation. So this is our supersaturation. This is the dimensionless quantity because this is equal to C by C star. It's just a ratio of concentrations. So grams per liter will get cancelled. So we get a dimensionless quantity. And J is it has a unit of nuclei per meter cube per second. And then maybe let me put it to small number so you can see the units clearly. So J, the unit is nuclei per meter cube per second, and then you have what we are going to do is like we are going to apply the classical nucleation theory. From there, so we have something like our supersaturation, and we have the nucleation rate. So as I said to you, nucleation rate should be in integers. So let's change it to integer. So roughly like when supersaturation is 2.57, the number of nuclei formed per meter cube of solution per second is 122. That's a big number, yeah. Like so in 2 seconds it will be double. In 3 seconds it will be double. It's going to only increase, yeah. So I think this is so far fine. So how to check this doubling factor? So 2 minutes it will be 2. Yeah, so this is a big number. Yes, in 1 second it's 122 means in 2 seconds it will be 122 multiplied by 1 plus 122, and it's going to multiply more and more. Yeah? At the end of 1 minute you will have more than, I don't know, nearly several thousands of nuclei in that unit volume of your solution. So that's how we calculate the nucleation rate. We are going to use these two values, the calculated values, and then we are going to calculate the Gibbs free energy. So in the exam you might expect some questions like that. So you must know how to calculate the Gibbs free energy and also the surface free energy. If I ask you to calculate, you have to calculate it for me based on this value. So I may give something like a time versus number of vials nucleated. From there you can roughly calculate the nucleation rate, and from the nucleation rate you can obviously calculate something like your Gibbs free energy and so on. Yeah? So I will go back to the paper tube. I will try to solve directly on the paper, and then I will also show you why we have the units of like a meter cube per second, and also what will be the unit of the surface energy, what will be the units of the other parameters involved in the Gibbs free energy. So so let's continue. I'm going to stop recording now, and then I will go back to the paper tube and try to watch and try to see how I calculated these values, like the P of t, which is in the F column, and then so from the experiment, all we are going to get is these two values, B column and the C column. C column is not even an experimental value. This is just the number, like a number of vials nucleated and at what time. So that's what we have. So 40 vials. We started the experiments with 40 vials. So we finished the experiment when all the 40 vials got nucleated, and we have to wait until you observe nucleation in all the vials. So that's the experiment, and that's how you calculate your nucleation rate. Yeah, I hope you all follow this one. So now we know how to get the nucleation rate as a function of supersaturation. So let me write the value of nucleation rate as a function of supersaturation. So your G value, S has no units, J has a unit of nuclei per meter cube per second. So in the exam, if you don't write the units, you will not get the marks. Yeah? So you have to pay attention to the units. So and supersaturation is 1.3, and there is 1.5, 1.76, 2.01, 2.26, and then 2.57. So the J value that we calculated is 14, 20, 27, 36, 99, 120. Normally this value will be an integer, so don't forget that. And then have to take the new notebook. So let's try to use the classical nucleation theory. So we know what's how to calculate the nucleation rate. So now we can calculate something which are difficult to measure using some analytical probe. For example, surface free energy. How to calculate that? Yeah, because some crystals are growing inside the solution. So how to get the surface free energy of the of those nuclei which is inside the solution, and also how to calculate delta G critical, how to calculate the critical free energy. So that's what we are going to do. So we all know how what's the classical nucleation theory is, exponential of minus delta G critical divided by K multiplied by T. So this is your classical nucleation theory. So and we know what is delta G critical is. So that's nothing but 16 pi surface energy raised to the power of 3, molecular volume raised to the power of 2, and then 3 kT multiplied by ln of S raised whole square, and then so that's our critical free energy. So let's call this equation 1. This has 2. Just plug the equation 2 in 1, so you will get something like a J is equal to A into exponential minus 16 pi sigma cube E square 3 kT ln of S the whole square into 1 by kT. So this is some expression. This is nothing but your classical nucleation theory. So what we have here, we have Boltzmann constant, we have temperature, we have molecular volume, and then we have to calculate this value, surface free energy. And then if we have all of this value, then obviously we can even calculate the critical free energy. So how to, and we also need to calculate this pre-exponential factor. So I will tell what is this pre-exponential factor later. I already explained this in the previous the lectures where I talked about this free energy, Gibbs free energy, and so on classical nucleation theory. I think that's the title of the lecture. Try to watch it if you don't remember. So k value, this is a very small number. It's somewhere around 1.38 multiplied by 10 to the power of minus 23. So it's extremely a small number. Unit is joules per Kelvin. Temperature is expressed in Kelvin. This is 15 plus 273. So that will some give your number in Kelvin. Then your volume is a molecular volume of the salicylamide. So typically it will be in this range of the magnitude will be around 10 to the power of minus 28 cubic meters. So we have to calculate this surface free energy, and then we also need to calculate critical free energy. So these two values we cannot get, just like we cannot take some vial and then put some analytical probe and then calculate delta G. No way. No, this is something we have to calculate based on the theoretical knowledge that we gained so far. We know classical nucleation theory. We know the how to define a critical free energy. If we know both of these theories, then obviously we can calculate these two parameters. It's very easy. So all we need to do is we have, let's call this as equation 3. Let's expand the equation 3. So take natural log on both sides, natural log of a, and then say plus minus 16 pi v square. Maybe I can even put something like v square divided by 3 k cube t cube ln of s the whole square. Okay, put. So this is something, if you expand you will get this value. So you already have a 3, it's like a 3k square t square multiplied by kt. That will be k cube and t cube in the denominator. This is a base simple formula. So if you want, we can rewrite this for sake of convenience. Ln of a. So we know let's take the known quantities, something like 16. We know the value of pi. We know the value of molecular volume. So divide by 3. We know the value of Boltzmann constant. We know what's the temperature. So we put everything together and then we have to calculate the surface free energy divided by ln of s the whole square. So if we plot this natural log of nucleation rate versus this quantity 1 by ln of s squared, or sorry, the constant divided by ln of s squared, then the slope value should be equal to minus sigma cube. So how to do that? So what do I mean by that? It's like maybe if you want I can rewrite in a more simple way. Ln of a plus minus 16 pi v square 3kt k cube t cube ln of s the whole square multiplied by sigma cube. So if we plot natural log of g versus 16 pi v square 3k cube t cube ln of s the whole square, you will get some points like that, and then you take the best fit line. That slope should be equal to negative sigma cube. So from that we can calculate the surface free energy. So that surface free energy will be equal to slope raised to the power of 1 by 3. So we have already the j value and we know all these values what is k, what is t, and so on. From that we can calculate the surface free energy, which is sigma. So before that, what's the unit of the surface free energy? So if you are confused what's the unit of free energy, we can even solve it using the classical nucleation theory. So j unit is like nuclei per meter cube per seconds, because we expressed time in seconds. And then A is something like a pre-exponential factor that has same unit, some number divided by meter cube per second. So if you remember, when I talked about classical nucleation theory, we have some molecules, they come together to form something like a clusters. We call them as pre-nucleation clusters. And then when each of these clusters, when they reach the critical free energy, when each of these the pre-nucleation cluster, when they reach the critical free energy, then they will evolve into a stable nuclei. So this is something like a something related to your the number of nuclei formed per unit volume per unit time, but this is something like a pre-nucleation stage, something that describes how much molecules they come together to make some number of clusters which may evolve into a stable nuclei. So both have same units. So if that is the case, so if the left hand side of the equation, if the unit is like say some number per meter cube per second, the right hand side should be equal to some number per meter cube per second, and we know a this unit is number per meter cube per second, which means whatever the other side we have, that should be a dimensionless quantity. Only then number per meter cube per second, number per meter cube per second will get cancelled. So let's solve the equation, the units for all the parameters inside this bracket. So what we have in this bracket is minus 16 pi sigma cube v square 3k cube t cube ln of s the whole square. So we know so let's solve this unit. So sigma cube, we know the molecular volume we express in terms of meter cube raised to the power of 2 divided by Boltzmann constant is expressed in joules per Kelvin, so joules cube divided by Kelvin cube multiplied by temperature is expressed in Kelvin, so Kelvin cube. S has no dimension, so just a hyphen. So Kelvin cube get cancelled. So you will end up with sigma cube meter 6 divided by joules cube. So so when this quantity will become dimensionless, when your unit of force, let's write sigma 6 meter, sorry, sigma cube meter 6 divided by joules cube. So when sigma unit is something like a joules per meter square, so if you substitute this value here, joules per meter square raised to the power of 3 m raised to the power of 6, and then joules raised to the power of 3. So joules cube by meter 6 by joules cube, they get cancelled, so it will become dimensionless quantity. So the unit of your surface energy is just joules per meter square. So why do we calculate all these things? So what you should know at the moment is like, if you're using the classical nucleation theory, if you're expressing your Boltzmann constant in terms of joules per Kelvin, temperatures in Kelvin, and then uh, what else we have, temperature, molecular volume in terms of meter cube, then automatically whatever the surface energy you calculate, that unit will be equal to joules per meter squared. So keep these things in the mind. So so let's do the calculation. If you go back to this expression, so what we are going to do is like, we are going to plot ln of g and this quantity. So I already calculated this value, so I can write it for you. Let me check my Excel sheet. So we have our supersaturation, we have J value, and then we have ln of J value, and then we have here like that the too many parameters, 16 pi molecular volume raised to the power of 2, 3k cube t cube ln of s raised to the power of square. So s is equal to 1.3, 1.5, 1.76, 2.01, 2.26, 2.57. So the j values I already showed you how to calculate 14, 20, 27, 36, 99, 122. So all look good. Then ln of j will be 2.614, 2.973, 3.2807. You can calculate yourself in the home. 4.599. So since I already calculated, I'm just adding the numbers here, and then this value will be some big number. So why this value is a big number? If you look at this equation here, say like 16 pi 3k cube t cube ln of s whole square. So even if you have a small value here in the denominator, here you have a k value, which is something like 10 to the power of minus 28, sorry 23, you raise to the power of 3. So automatically you will have a massive number here in the numerator, the ratio. So that's why normally this value will be a big number. If you see some very heavy number, don't get scared. That's completely normal. So you get 3875 2907 1622 5821 834 7078 5473 123 4012451. You can calculate using Excel sheet. It won't. So I already gave you the values. K value T is 15 plus 273. That's it given in Kelvin. Then you have molecular volume. Volume is 10 to the power of minus 28 meter cubes. So all you need to substitute these values, and then you get these numbers. But if you plot ln of g versus this big the quantity, which is we just calculated, 16 by 3k cube t cube ln of s whole square. So you will get some points like that. So try to get the straight line. That slope, whatever that slope, that will be equal to sigma cube. So it will be negative slope minus sigma cube equal to, I got a value of minus 1 e power or minus 1 into 10 to the power of 7. So if you take the cube root, sigma cube 1 into 10 to the power of plus 7 to the power of 1 by 3, sorry, minus 7, 10 to the power of minus 7. Oh, no, I think I got a value of minus 1 plus 7. Let's calculate it one time using my calculator. There is something wrong in this calculation. Getting some wrong numbers. 16 pi k cube t cube into ln of s square. Let me calculate it one more time. So you have 16 pi 3.14 into volume raised to the power of square divided by 3 times k Boltzmann constant. I think I did a mistake when I was plotting. That's why it took some time. The calculations were completely fine. So all I need is to plot correctly ln of j on the y-axis and then the other parameter on the y-axis, sorry, x-axis, 3k cube t cube ln of s the whole square. If you plot them correctly, you will get something like this. So try to plot it yourself. So try to use the Excel sheet. That's very easy to plot this type of graph. Since you're going to write the exam from home, better I prefer you to use the Excel sheet to get this type of to perform this type of calculations. Yeah. So the slope or the equation will be something like that. This trend line ln of j will be equal to minus 5 into 10 to the power of minus 8, your x value, which is nothing but the whole parameter here, plus 4.274. So what does this mean? So ln of a, that is 4.274. Therefore a will be equal to exponential of 4.274. That will be equal to, let me calculate, somewhere around 71,80829. So just put 72. This should be some integers. Yeah. So this is something related to your pre-nucleation clusters. So many clusters are forming per meter cube per minute, and eventually your nucleation rate is only, so that's for this particular system. Yeah. So somewhere around 71 pre-nucleation clusters per meter cube per minute. So that's the meaning out of that. So and then what is this? You have a slope value. So sigma cube minus sigma cube will be equal to minus 5 into 10 to the power of minus 8. Therefore, sigma will be equal to 5 into 10 to the power of minus 8 raised to the power of 1 by 3. So the value will be equal to 0.003896 millijoules per, joules per meter square. So if you want, you can convert it into millijoules. It will be around 3.896 millijoules per meter square. So that's how we already calculated the surface free energy through this method. And then we even calculated the pre-exponential factor. And the pre-exponential factor, it should be, it has the same unit of your nucleation rate. So 72, something like numbers per meter cube per unit time. So in this case is per second, as we express the time in seconds. So if you want, we can even calculate the delta G critical. This is very simple. We know the formula for delta G. Let me check one time. So don't want to do any mistake. It's 16 pi sigma cube molecular volume raised to the power of cube kT ln of s the whole squared. So we have all the values. We calculated the surface free energy. We know the molecular volume, everything. So it will be equal to 16 multiplied by 3.14. The sigma value just now we calculated 0.003896. Pay attention to the units. So this should be joules per meter square. Then your molecular volume should be in meter cube. So that's 10 to the power of minus 28 whole square divided by 3. Your Boltzmann constant, I think 1 point. Oh, I should remember this Boltzmann constant. If I don't remember, it's a shame, and I don't remember. 10 to the power of minus 23 into our temperature is 288 Kelvin. Our temperature is 288 Kelvin multiplied by, let's calculate the free energy when supersaturation is 1.3. So let's say ln of 1.3 the whole square. So whatever the value that you get, that will be the delta G critical at supersaturation of 1.3. So hope you all follow up to this point. So I think that's it. We finished the problem. So why I showed this experiment is like, normally if you go to your textbook, normally they have some problem say like somebody crystallized paracetamol in some solvent, say isopropanol, and then the nucleation rate is something like 10, or something like maybe select 10 to the power of or maybe 100 meters, like numbers per meter cube per second at a supersaturation of 1.1 and so on, like, so you will never know how this j value is obtained, and you will never even realize that j value is something related to the or j value is some number that can capture the stochasticity in the nucleation process. So that's why i I showed all the experiment, how we perform the experiment, how we, when we know some system is nucleated, how do we rely on our eyes, and what's mean how the solution changes from the clear solution to the cloudy solution, and we use that as an indicator, as a point of nucleation, and so on. And you also know how to use a probability function, and you know how to experimentally get, like, if all the 40 vials are nucleated, that means, like, at that particular time 100% nucleation can be expected, or if you want you can say, like, for that particular system or that particular supersaturation, nucleation is more likely at at that particular time, or least likely at at some particular time. So these are some concepts that you should think about nucleation. And nucleation is like one of the most widely used technique in pharmaceutical industries, and they use this technique mostly to purify or to get some compounds with with some specific crystal structure. We call it as a crystal polymorph. So nucleation is a very good technique, and it's also widely used purification technique. So that's why we are learning this in big detail. And also the salicylamide itself is of interest for pharmaceutical industries. So I think I'm going to stop now, and then this video is going to be a bit heavy for you, because I recorded video here and there, and then I have to put them together. So it's going to be heavily edited video, but it's worth learning this nucleation. And I'm very happy that I finished this module with this very good example of nucleation, because this is something I do in the lab, and this is one of my favorite topic, and I like to to show you this topic before finishing this module. So try to solve this problem yourself. You have the data. I will also upload the Excel sheet, so you can have a look at the Excel sheet which I used for teaching this particular tutorial, and then you see how I solved it using the Excel sheet, and that will be a good practice for you. In the exam, you might expect some questions on this topic, yeah? So be ready for that.